Okay, so let's look at another concept called sampling distribution. So we already have studied the population sample, and we know that sample statistics are more convenient to study rather than working on the entire population. So what we do is whenever we're you can say extract data from the population and plot it on the normal and plot the normal distribution of the data, what we do is we select n samples. N is a certain number which we will discuss later on, and we extract n samples from a population, and the size of each sample should be at least 30 or greater than 30. So we then calculate this n sample means and then plot their distribution and study the distribution. To understand this concept and to go through the entire procedure, let's look at an example. So we already know that the population is a set of all values or measurements from your experimenting space. So in this example, our experimenting space is the world, and the population is the life expectancy data from all countries, and the population size is n. So then we have to sample the data from here, and the sample should be selected randomly as a subset from the population, and the sample size will be denoted by n, and the distribution which will be described is the data population and sample range and how the data is spread in that range. Distribution of life expectancy in the world as of 2018 will be represented in this figure. So you can see that the population and the distribution of the population data, which represents the average life expectancies after 2018, is plotted over here. The histogram is plotted. We have not drawn the curve, the bell curve of the normal distribution, but you can still ask yourself, is this a normal distribution? It's not entirely, you can say, a normal distribution. It is a bit skewness. There is a bit skewness towards the left side. So I can say that this is not a perfect normal data distribution. So when we draw the figure, and we see that this is not the perfect bell curve and the median is not equal to the mode. You don't have to calculate the median or the mode, although we actually do that, but even without doing that, we can, by looking at the figure, we can see that there is a left skewness, or you can say the negative skewness, and which shows that the data points are more concentrated on the left side. So let's take some samples from the population. In other words, let's make 1,000 subsets and each of the size of 150 from the population and plot the distribution of each sample's mean. So we take 1,000 subsets and the size of each subset is 150, and we calculate the mean of each subset, and after that we plot those means in the form of a histogram, and then we study the distribution of these sample means. As you can see, this is a perfect normal distribution. Actually, that is what we are trying to study over here, is that any sampling distribution from any population shows normal distribution. And this is a concept which will be studied as the central limit theorem. So regardless of the initial shape of the population distribution, sampling distribution will approximate to a normal distribution. So the condition for that is the sample size increases, the sampling distribution will get narrower and more normal. So that's why we have the condition over there before. We saw that the n should be greater than or equal to 30, and if we go less than that, we will somehow disrupt our approximation. So the sample size should be greater than or equal to 30. Okay, so now I want you to relate this concept with inferential statistics. We studied that we wanted to infer our learnings from the random sample dataset to the generalized population. Now we saw that if we approximate the sample means of subsets of these random sample subsets, we will approximate it to the normal distribution, which will have the mean that is shown in the population. Because even though we have the population data and distribution in this example, but in reality we would not have this type of population data. We will only have sample data sets. So let's go over the number of steps once again. Firstly, we select a number of subsets, and then after selecting those number of subsets, each subset should have at least 30 size or greater than that, and then we calculate the means of each subset, and then we plot them on the histogram, and then we study the distribution. It will always approximate to the normal distribution, and that is when we will get to see the mean, median, and mode, and other types of information we can get from the sample means as well. So the central limit theorem would be the reason or the essence we can get from the central limit theorem is that we calculate the population and sample mean, and the population and sample mean is equal, should be equal whenever we're doing that. So if we have a sample data set and we apply the central limit theorem, we get the mean. Its mean can be approximated and is equal to the population mean. So first information we can generalize about the population is its mean. The second information we can generalize is the variance, because the population and sample variance can be approximated by the fact that we can calculate the standard error. The standard error is when we divide the standard deviation by the square root of number of samples. So we get the standard error. So the conditions for the sample central limit theorem is that whenever we are sampling data set, the sample size should be greater than or equal to 30. Why? Let's look at an example to further illustrate this. So the population distribution looks like the topmost row. So when we plot the population distribution, we have three examples. These three examples look like this. So whenever we sample a distribution of X and we calculate the means and we sample the means, let's say n is equals to 5, which is less than 30. So what happens is that we can see that these figures do not actually approximate to the normal distribution. But as we increase the value of n, the sampling distribution of the mean approximates the normal distribution. So it becomes pretty clear that the key over here is the sample size. So as we increase the sample size and the number of total sample subsets, and each subset should have at least the size of 30. So let's talk about confidence intervals. Confidence intervals, you can say the position or the area under the graph which tells us the confidence level of how much you're confident about a particular distribution. It has a lower limit and an upper limit. And you can say under the normal distribution, this particular region under the curve shows us that you're 95% confidence that the mean and the other values lie in this particular region.